Hello there, I am Sonal Kumar. This presentation will discuss one of our papers titled Iterative Pseudo-Supervised Contrastive Learning to Improve Self-Supervised Feature Representation. This paper explores the possibility of improving the quality of self-supervised visual feature representations. We presented this paper in ICASSP 2024. In an unsupervised setting, manual annotations are not available. Self-supervised learning enables a deep learning model to learn with an unlabeled dataset. The two major stages of self-supervised learning are pretext task and downstream task. The pretext task is a predefined task to perform unsupervised training. The deep learning model learns meaningful and discriminative visual representation by solving a pretext task. The nature of the pretext task could be predictive, contrastive, or generative. The downstream tasks are computer vision applications that utilize the pre-trained model from the pretext task stage, like image classification, segmentation, etc. Recently, the SimCLR method proposed a batch contrastive approach as a pretext task. Without manual annotations, the SimCLR framework first generates multiple views of each image in a batch with an image augmentation strategy. Later, it trains the underlying model using contrastive loss to bring the feature representation of an anchor image closer to the feature representation of its views and apart from the feature representations of the views of other images in the batch. Due to its capability of learning semantic information from unlabeled images, it outperformed the initial photometric or geometric prediction-based pretext tasks. Even if the batch contrastive approach like SimCLR generalizes well across deep learning architectures, tasks, and datasets, it heavily depends on the data augmentation strategy. Recently, a supervised counterpart of the batch contrastive approach has been proposed. It replaces the augmented image or views of anchor images with images sharing the same class label. Images of the same class have higher intra-class variance than different views of the same images. Hence, a supervised contrastive learning outperforms the unsupervised counterpart. Based on our observation, we argue that introducing intra-class variance in an unsupervised batch contrastive approach can further improve the quality of visual features. However, in an unsupervised setting, we must address several challenges to introduce intra-class variance in a batch contrastive approach. For example, the class-level information is not available. An alternative could be utilizing pseudo-labels, but it also suffers from noise labels, class imbalance partitions, and random initialization. To overcome these challenges, we propose an iterative pseudo-supervised contrastive learning method with two major contributions, a pseudo-label generator and a pseudo-supervised contrastive loss. The pseudo-label generator iteratively discovers the underlying partitions in an unlabeled training dataset. It utilizes the scan framework, and its encoder is updated after each iteration. Here, one iteration signifies a fixed number of training epochs. The pseudo-supervised contrastive loss captures the benefits of both image augmentations and pseudo-label information from pseudo-label generators. It is a convex combination of unsupervised and supervised contrastive loss, and lambda controls the contribution of each part of the loss function. An unlabeled dataset is initially input to the pseudo-label generator to discover the underlying partitions. Next, two augmented views are generated for each training image in a batch, and an image with the same pseudo-label is fetched from the discovered partitions. Finally, the unsupervised part of the loss function minimizes the distance between the anchor image and its augmented views in feature space. Parallelly, it maximizes the distance between the anchor image and views of different images in a batch. The supervised part of the loss function minimizes the distance between the images from the same pseudo-class and maximizes the distance between the images from the different pseudo-class in visual feature space. Before each iteration, the encoder of the pseudolabel generator is initialized with the updated encoder and trained for a few epochs to update the existing partitions. Notably, the pseudolabel generator's encoder is randomly initialized in the first iteration. Hence, we set the alpha value of pseudo-supervised loss to 0 for the first iteration. We have experimented with two popular datasets Cypher10 and STL10. Finally, the effectiveness of learned visual feature representation is evaluated in two ways: k-nearest assessment and unsupervised classification as downstream tasks. Tables 1 and 2 show that Ipcl outperforms the baseline method, i.e., SimCLR. Table 3 suggests that a smaller alpha value is favorable for effective training. Table 3b shows that a large period between two consecutive iterations is preferable. Table 3c suggests that a shorter scan training time is sufficient to discover meaningful partitions. Finally, the graph shows that the quality of the underlying partition improves in each iteration. Thank you. Please scan the QR codes below to read our paper, connect on LinkedIn, and access the GitHub repo.